So for sorting, we have seen many different algorithms. The basic idea behind each of the algorithms will be different. So we can categorize the sorting algorithms as incremental sorting or the basic brute force method of sorting. So in that we are having insertion sorting, bubble sorting, and selection sort. Okay. And then we are having bucket sorting. Okay. So based on the digits position, the values will be placed in multiple iterations, and then we can get the list sorted. Okay, like counting sort or bucket sort. And the other technique is using the divide and conquer method. So in divide and conquer method, we have two types. One is merge sort and another one is quick sort algorithm. So in merge sort algorithm, how do we divide the list? That is, we are dividing the list by half every time. Okay. So we are not considering the values to divide the array. Instead, just based on the count, we are dividing them. So while dividing, we don't look at the values. Just by the count of the values in the array, we are dividing them. And once I get a list of size which need not be splitted further, then we apply some basic sorting. Then we start merging them. So during the process of merging, we have the comparison. Then based on that, the value is getting sorted. Okay. So in merge sort, whether I am having the best case input, whether the input is already sorted or randomly sorted, the running time will always be n log n. It is constant. Okay. But the problem with the merge sort is, if I'm having an input in an array, say for example in A, to merge it, I have to use another one array of the same size. Okay, another B array should be used. So the space complexity will be more. That is usually in other algorithms. Within the array itself, we are swapping the values. So I don't create an extra array to copy the values. But in case of merge sort, that is the issue. That is the challenge we are having. The space will be more compared to other sorting algorithms. Okay. But the running time is the best that we are having, because even in the worst case, the running time will be n log n. So the another variety of divide and conquer method is quicksort method. So in quicksort, the same thing, we are dividing the array into two parts. Okay, we are not dividing them into two halves. That is in case of merge sort, because it is by the number of values. But here in quicksort, we are partitioning or dividing the array based on the value. Okay, so we look at the values and we choose one of the values as the pivot value. Okay, and based on that pivot, we are separating them into two partitions, where one partition will be having so one partition will be having values lesser than the pivot element. So I have chosen some P as the pivot position. So the partition at the left side will be having lesser values than the pivot, and the other side will be having greater elements. Okay, so the pivot element will be lesser than the right side element. So in that way, based on a particular value, we are partitioning. So initially when I'm having n elements, one value I'm choosing as the pivot, based on that I'm dividing. So now I'm getting two portions, first portion and second portion, left of pivot and right of pivot portion. But it is not guaranteed that the array is getting divided into two halves, because randomly we are choosing one pivot value, and based on that I'm dividing it. Okay, so it need not be the middle value. The random chosen element need not be the middle value of the given set of values. So the array will not be partitioned into two halves exactly. But whether it is two halves or any size, we apply the same logic for the left part of the pivot and right part of the pivot. So this is getting repeated till the whole array is getting sorted. So when I'm doing this here, when I'm doing the partition, I'm doing the comparison. If you remember the merge sort, it is doing the comparison when it is merging the array, okay, merging the subparts. But here, for dividing the array into the subparts, it is doing the comparison. Okay, so that is the logic of quicksort algorithm. Okay, so actually to attain this, to divide the array into two partitions based on a particular pivot value, two ideas can be used. And comparatively, coding part of this particular idea, what we are going to see is simpler. Okay, anyway, after this, I'll explain the other method also. Whichever is suitable for you, whichever you are comfortable with, you can choose that. Okay, fine. I'll go with an example here. So now we are having some 7 elements to be partitioned. Okay. So we are having n equal to 7, 7 values to be partitioned. And I have to choose one pivot value. Okay, one driver value I have to need. Based on that, I'm going to split this into two parts. So let me, in my algorithm, let me always choose the last value in the array to be the pivot element. So let me choose this as the pivot value. Okay, so this is my pivot value. Now, what should I do? All the values which are less than 40. So if I take less than 40 means I'm having 20, 35 and 25. This should come to the left side of 40, and the greater values 45, 60 and 50, that should go to the right side of 40. So in that way I have to split. So what logic here we are going to use is, I'm going to use two iteration variables. One is I and let the other be j. Okay. So now the positions are okay. So from 0 to 5, I have to compare. Okay, 6th is the pivot element, and from 0 to 5, I have to compare with 40, and I have to rearrange. So what I'm going to do is, I am going to initialize. This is my, since here the recursive function we are going to do for this also, as in the case of merge sort. Instead of passing the number of elements, we are going to pass the left end index and the right end index. Okay. So I have taken the rightmost value in the array as the pivot position. So if this array is named as A of R is taken as the pivot. Okay. So pivot is A of R. Okay. And then I'm going to start this J from L value. Okay. From 0th position onwards, I'm going to compare with the pivot value. Okay. So J is going to start with L, and then it will go L plus 1, L plus 2 up to this R minus 1, it will move. Okay. And compare with the pivot element. So let me use a for loop. For it will be from L to R minus 1. Okay. So what I'm going to do is, I'm going to compare this 45 with 40, and 45 is greater than 40. Okay. If it is fine. If I'm getting, next time I'll move to this position. Okay. J is starting from, J started from 0, and 45 is greater than 40. Fine. I'll move to the next position. J will move to next position. Next I'm getting 20. 20 is lesser than 40. Now I have to split the array so that left side should be lesser than 40 and the right side should be greater than 40. But here I'm having 45 greater than 40, but 20 less than 40. So I'm going to move this 20 to the left side, and the 45 should be moved to the right side. So I'm using another one variable which will be initialized with the value L minus 1. In this case, it will be minus 1. Okay, L is 0, hence I will start from minus 1. So I starts from minus 1. When J encounters a value which is lesser than the pivot element, then I'll increment this I by 1. Okay, I will be incremented by 1. So now currently J is here. Okay, J is here and I is out of the array. It's not in the bound of the array, it is out of the bound, and I will be incremented by 1. So I will come to this position. Okay, and we will swap A of I and A of J. Okay, so every time the A of J will be compared with the pivot element, and when A of J finds an element which is lesser than the pivot, that value will be swapped with I plus 1 value. Okay, so now I is incremented. Now this will be swapped with J. So it becomes 45. Okay. Now we continue. I stopped here. Okay, after swapping, then J will move to the next position. J will be here. Now 60 is greater than 40. Greater than means no worries. We have to move further to the right side. Then again, J will be moving to next value. Now I am getting 35. Now 35 is lesser than 40. So when I get a lesser value than 40, then I have to swap with the I. So what should be done? The I should be incremented to next position. I will be here. Okay. Now J value and I value will be swapped. Okay. So what happens? 35 and 60 will be swapped. Okay. So now if you observe, I is at this position 35. Okay. I is at 35, and after swapping it with 60, J comes to this position. If you see here, till this I, okay, till this I, what values I am having? 20 and 35. 20 and 35 are lesser than 40, lesser than the pivot element. And from I plus 1 till this J, before J, I am having the values, sorry, here it is 45, right? So it is swapped with 45. This 45 is moved here. So 45. So after I plus 1 till J, I'm having the value 60 and 45. They are greater than pivot. Okay. From J onwards, I haven't yet checked. They have to be checked yet. Okay. Now again, I'm comparing 50 and 40. 50 is greater. If A of J is greater, just move to the next position. So J will move here. And now I'm having 25, and 25 is is less than 40. In that case, I have to swap J with what? Can you text? Or you may switch on enable your mic and tell. 25 should be swapped with 25 should be swapped with. The logic is simple. We are checking A of J. We are comparing A of J with pivot. If A of J is greater than pivot, J is just moving to the next position in forward direction. And when J is getting a lesser value, then Jth value should be swapped with I plus 1 value. Okay, now I is here in 35, that is in position 1. So I will be incremented to the next position, and this J and I will be swapped. This 2 will be swapped. Okay, so we'll be getting 25 here and 60 here. Okay, now again, if you see, J has reached R minus 1. J will be going up to R minus 1 only. So J reached its destination. So the iteration stops. Now what do we observe here? From L to I, I'm having lesser values than 40. Okay, I'm having the values 20, 35 and 25. Then from I plus 1 to J, I'm having the values 45, 50 and 60. Okay. So now I'm having the 40. Now 40 should be placed in between this, between the lesser values and the greater values. So I'm going to swap this 45 with 40. So 45 will come here and 40 will be placed here. So to which position I am swapping this 40? I is here. Okay, and J is here. And 40 should be swapped with which position? Based on I and J. What should be swapped with? I plus 1. Okay. Okay, I plus 1 will be taking the pivot element. Okay, hope you are listening. So let us code this one. Okay, so j is starting from here. Initially, what value we have given for I? I was given with L minus 1. So I is taking the value L minus 1 and j starts from here. So we are checking if A of j is less than only we are swapping. Otherwise, we continue. So if A of j is less than or equal to pivot value, then we are swapping. I should be incremented. I should be incremented by 1 and we have to swap A of j and A of I. Okay. When I'm getting a great lesser value, we swap I and j and then move to the next position. So this loop continues. When the loop gets over, where do we place this pivot element? In the next position of I, we are placing the pivot element. So we have to swap A of I plus 1 and A of R. Okay, and at the point where I'm splitting, that has to be returned. So where I'm splitting the array, at position I plus 1, I'm splitting the array. So that position has to be returned. So this is the procedure used to partition the array. In merge sort, we are having the logic to merge the array. There we are doing the comparison. Instead here, we are having the logic to split the array. Okay, fine. Now this is to do the split one time, but this has to be repeatedly done. So there should be one recursive function which has to drive this partitioning function. So for that, there will be a recursive function which will be taking the input as the array and the left limit and the right limit. And in this, first I have to partition. So I have to call this function. Let the function be named as partition. Okay, to which I have to pass the array, the left end and the right end. Okay, now this is the algorithm I'm having for partition. Okay, which is receiving A, L and R. Okay, and once this is completed, this I plus 1 is returned and that is received here in P. Now again I have to call the quicksort function, the same function. This has to be called. Now with the values A, then from L up to P minus 1, this function has to be called. Okay. Similarly, the same function has to be called from P plus 1 up to R. Okay. So that's simple. The quicksort is okay. So this is what the quicksort program is. Okay. So I'll revise the algorithm logic. We are initializing I as L minus 1 and the last portion, last element in every partition is taken as pivot element. Then we move from L to R minus 1. This is L, okay, L to R minus 1. Then we compare jth element with pivot element. And if jth element is less, then we have to increment I and then with that we have to swap j. After the loop, then I plus 1 will be swapped with R so that the pivot element is made to the between portion of the left lesser value and the greater value. And then we have to return I plus 1 where pivot element is placed. That position we are returning. So in the main quicksort algorithm, we are calling the partitioning function by passing this left end and the right end index. And once this position is known, pivot position is known, the quicksort is again applied for left end to pivot minus 1 position, then right end to, partitioning position plus 1 to right end. And this has to be repeated when L is less than or equal to R. The left index is less than R. The same condition used for doing the merge sort also. Okay. So this is what quick sort is. And the complexity is the complexity of the algorithm is if the algorithm is getting divided equally every time, okay, then the complexity of the algorithm will be the time of the algorithm for the input of size n will be it can be represented as a recursive function, a recurrence relation as here 2t of n by 2 plus big theta of n, and if we solve this we'll be getting the value as n log n. That is as in the case of merge sort. In the best case also it will be getting the time as n log n, but in the worst case it will be having its time complexity as n square. Okay. The complexity will be n squared. How it is when we'll be getting that is if the input is already sorted. The worst case input will be sorted input. So if I'm getting the sorted input, I'll be taking the last element as the pivot element. So every value will be lesser than the pivot value. So when I'm partitioning, left end will be empty and the right end will be having the remaining values. So one end is nothing to be done, and in the other end, again, the same process has to be repeated. That is, if I'm having the values as 1, okay, this is the value. So this will be taken as the pivot element. When I'm comparing this with all the elements, this 5 is greater. So the left end will be empty, nothing will be there. Okay, and the right end will be having 1, 2, 3, 4. And again, for this, when we apply, this 4 will be chosen as pivot. Again, there is nothing to be divided. All the elements are lesser than this. Sorry, left end will be less. So if I'm having sorted ascending ordered element, then all the elements will be lesser than 5. So the left end will be having all these values and the right side will be empty. Okay. And again, if the algorithm is called for this portion, this will be taken as pivot and left side will be having remaining values and the right side will be empty again. Okay. So this will be continued. So we are doing the comparison every time. The n comparisons will be done for every smaller size of the array. So it will lead to the normal other bubble sort, insertion sort algorithms, and it will be getting its complexity as n square. Okay. So the worst case complexity will be n square, and in the best case it will be having the complexity as n log n. Okay. And in the other idea, how we do is we'll be choosing again any one value as the pivot element. And here in this example, the first element is chosen as the pivot element. And we will take two references. One reference will start from the left end and another reference will start from the right end. In our case, in the earlier example, we had both I and j starting from left itself. But here, if I take this as I and this as j, I starts from left side and j starts from the right side. Now we'll be comparing the left end value with the pivot value. Left end, what do we need? We need the lesser values to be left side. So 3 is less than 5. Fine, it is correct. Then we'll move to the next one. Now 8 is greater than 8. Then I'll stop here. The left index will stop here. Okay. Similarly, the right index will start from here. Right side, I want greater values to be present. So 7 is greater than 5. So right will move here. And 2 is lesser than 5. That should not be. So stops there. So right and left stops here. So what do? We swap them. So what happened? 2 is taken here and 8 is taken here. Again, left will be moving here and right will be coming here. The same comparison will be repeated. When left and right crosses each other, right come to the left side and left come to the right side, that time we will stop. Okay. And at this position, the pivot value will be swapped. Okay. So here we are swapping it with this value. Okay, 4 and 5 will be swapped and we are getting this as the new array. So now here it is placed. This is the pivot element. Here it is placed. and the left side we are having 4 3 2 1, and the right side we are having 6 8 7. Again, the same process has to be applied for the left side and the right side. Okay, so this is another way of partitioning the array. Okay, we use two indices. One is starting from the left and the other is starting from right. The left will move if the values are less. When greater element comes, it stops. And the right will move to the left side. In the reverse, it is getting decreased. And if it is having greater value, it will get decreased. If it is having lesser value, it will stop. Then they are getting swapped, and this process continues. When we will stop is when the right and left are crossing each other. When right becomes lesser than the uh, left value, then at the right portion, the pivot element is swapped. Okay. So the core algorithm is the same, the driver algorithm is the same, but how we partition is different. Okay. So what do we do? Here we are taking, in this example, we have taken leftmost value as the pivot, and I starts from left portion, left plus 1, and j starts from the right side. And while I is less than j, we repeat. Then we are comparing a of I with pivot, and if it is less than pivot, I is getting incremented. Then we start comparing with jth element. If j is having greater element, j will be getting decreased. When the condition fails, it comes here. If I is less than j, then we are swapping I and j. Okay. So when this is completed, we are swapping the pivot position, L position. This is the pivot position, and the pivot position is swapped with the jth element. Okay, the right index, it is swapped. And at j, we have done the, we have made the partition, so j is returned. Okay, so either you can follow this algorithm, okay, or you can follow this algorithm. But the complexity of both the algorithms will be the same. In best case, it is having n log n, and in the worst case, it is having n square.